On June 27th, 2026, a mountain of rock will pass closer to Earth than it has in over 400 years, and after nearly 3 decades of watching it, we still cannot agree on the two simplest things about it. We do not know how big it is. The estimates run from 400 meters to 1.5 miles, and we do not know what it is made of because 3 different teams have read its light and come back with 3 different answers that cannot all be true. It will miss us by millions of kilometers, so this is not about danger. It is about something stranger. How does an object this large, this close, and this long known stay, this completely unidentified, right up until now? If that question grabs you the way it grabbed me, take a second to like this video and subscribe to the Sky Lab, where we follow these stories as they actually unfold. Drop a comment and tell me where you're watching from, and whether you'll be trying to spot this one through a telescope on the 27th. Now, let's get into it. Part 1. The object that won't hold still. Right now, as you sit there watching this, a mountain of rock is moving through the dark at tens of thousands of miles an hour, and it is pointed almost straight at us. It will not hit us. I want to say that plainly and say it early, because everything else I am about to tell you over the course of this video is going to make the back of your neck prickle, and I do not want you spending the next while braced for an impact that is not coming. On June 27th, 2026, this object will sweep past our planet at a distance of about 2.6 million kilometers. That is close in the language of space. It is a little under 7 times the distance to the moon. But it is still a gap so wide that nothing about this particular pass threatens a single person alive. And yet I think this is one of the most quietly disturbing objects in the entire sky. Not because of what it is going to do to us, because of what we still do not know about it. The object has a name, of a sort. Astronomers call it 1997 NC1, and in the official catalogues it carries a permanent number as well, 152637. The name tells you the one thing we're sure of, which is when we found it. We first spotted this thing in the summer of 1997. That is almost 30 years ago. For nearly 3 decades we have known it is there. We have watched it loop around the sun and come back again and again, and we have stamped it with one of the more ominous labels in all of astronomy. It is officially classified as a potentially hazardous asteroid. That label is not handed out lightly. It is reserved for objects that are both large enough and on orbits close enough to ours that we have decided, as a species, that we had better keep an eye on them. So here is the part that should bother you. After 29 years of watching, after nearly 3 decades of pointing some of the finest instruments humanity has ever built at this single moving dot, we still cannot agree on 2 of the most basic facts about it. We do not know how big it is, and we do not know what it is made of. Those are not exotic questions. They are the first 2 questions a child would ask. How big is it, and what is it? And the honest answer, after all this time, is that the experts genuinely disagree, and they disagree by enormous margins. When I say we disagree about the size, I do not mean we are quibbling over a few meters. Estimates for the width of this object run from about 400 meters on the low end to as much as 1.6 kilometers on the high end. Sit with that for a second. That is the difference between something a few city blocks across and something larger than the Golden Gate Bridge is long, a structure you could not walk across in 15 minutes. We have tracked this rock for an entire human generation, and we cannot tell you whether it is the size of a sports stadium or the size of a small mountain. The uncertainty is not a rounding error. It is a factor of 4 in width, which means it is a factor of dozens in mass and in raw destructive potential. We are not arguing about the details. We are arguing about what kind of object this fundamentally is, and the reason we cannot answer is, in a strange way, the most fascinating part of the whole story. Because it turns out that finding an asteroid is the easy part. Knowing what you have found is the hard part. When you look at an object like this through even a powerful telescope, you're not seeing a little world with mountains and craters and a shape. You're seeing a single point of light, one dot, a faint smear of reflected sunlight crawling across a field of stars. That is all. Everything we claim to know about the size and the nature of these objects, we have had to wring out of that one dot, and the dot, it turns out, can lie to you in ways that are not obvious until you understand how the trick works. That is what makes this dune so important, and it is why I genuinely could not let this one pass without sitting down and walking through it with you. Because this flyby is not just another close approach. This is the closest this particular object has come to Earth in over 400 years. To put a finer point on it, the last time 1997 NC1 was this near to us, it was the early 1600s. There were no telescopes pointed at the sky that could have caught it. Galileo had barely turned his first crude instrument toward Jupiter. The entire science of astronomy as we know it had not been born yet. This object has been waiting, in effect, for 4 centuries to come back into range, and it is coming back into range in a window measured now not in years but in days. And because it is coming this close, we are finally going to get to do something we almost never get to do. We are going to be able to bounce radar off of it, not just watch its faint glow, but reach out and touch it with a beam of radio energy, listen to the return come back, and from that return read its true size, its true shape, and finally, after 30 years of argument, settle what it is actually made of. Within days of this flyby, a mystery that has stood since the 1990s could simply collapse into a known fact. We could go, in a single night, from arguing about whether this is a 400-metre object or a 1.5-kilometre object, to knowing the answer to within a few metres. But I want to be honest with you about why I find this object haunting, and it is not really about this rock at all, it is about what this rock represents. Because 1997 NC1 sits, depending on which size estimate is right, squarely in the size class that the people who study these things consider capable of ending human civilization, not damaging a city, not flattening a region, ending the world as we have built it. And the thing I cannot stop turning over in my mind is this. If an object that large, that close, that long known, that officially flagged as hazardous, can stay a genuine mystery to us for 30 years, then what does that say about all the objects out there that we have not tracked for 30 years? What does it say about the ones we have only just found? What does it say about the ones we have not found at all? That is the thread I want to follow with you tonight, and I want you to hold on to it, because everything in this video hangs from it. We are watching a single object come closer than it has in 400 years, and we still cannot say what it is. So before that radar beam goes out and the answer comes back, I want to understand exactly how we ended up so uncertain about something so close. I want to understand what that single point of light has been trying to tell us and why we have had such a hard time listening. Because the story of why we cannot measure this asteroid is quietly the story of how little we truly see of the sky above us. And the first clue is hiding in plain sight, in the one thing we thought we understood best about it, which is simply how bright it is. Part 2. A single point of light. To understand why a 30-year-old asteroid can still be a stranger to us, you have to understand what an astronomer is actually working with when they study one, because it is so much less than people imagine. When you picture a scientist studying an asteroid, you probably picture a detailed image, a grey potato of rock turning slowly against the black, every ridge and crater picked out in sharp relief. Throw that picture away. That is not what 1997 NC1 looks like to us. It has never looked like that to us. What it looks like is a single faint point of light, no different in appearance from a distant star except that it is not fixed. Night after night it crawls a little further across the background. That crawl is how we found it. That crawl is how we know it is near and not light years away. But the dot itself gives up its secrets very, very grudgingly. Think about what that dot actually is. It is sunlight. The asteroid makes no light of its own. It is a dark, cold body drifting in the dark, and the only reason we can see it at all is that the sun is shining on it, and a tiny fraction of that light is bouncing off its surface and travelling all the way across millions of kilometres of empty space to land in the mirror of our telescope. So when we measure how bright the object is, we are not measuring the object, we are measuring the light it reflects, and right there, buried in that simple fact, is the trap that has held this asteroid secret for 3 decades. Here is the problem in its cleanest form. Imagine I show you a single point of light in a dark room, and I ask you how big the thing producing it is. You cannot answer. You genuinely cannot. Because a small, bright, mirror-like object can throw exactly as much light at your eye as a large, dull, charcoal-coloured object. A tiny shard of polished chrome and a great slab of black coal can look identical from far enough away, if the chrome is small enough and the coal is big enough. The brightness alone does not tell you the size. It tells you the size multiplied by the reflectivity, and those two numbers are tangled together in a way that a single measurement can never separate. Astronomers have a word for that reflectivity. They call it albedo. It is just a measure of how much of the light hitting a surface gets bounced back. A fresh field of snow has a high albedo. It throws back most of the sunlight that lands on it, which is why a snowfield is blinding on a sunny day and why it stays cold even in direct sun. A lump of charcoal has a low albedo. It drinks the light in and throws almost nothing back, which is why it bakes in the sun and why it looks black. Everything in nature sits somewhere on that scale, and asteroids are no exception. Some asteroids are bright, relatively speaking. Some are among the darkest objects in the entire solar system, darker than fresh asphalt, reflecting only a few % of the light that touches them. So when you find a new asteroid and all you have is that one point of light, you're stuck with a single equation that has two unknowns in it. You know the brightness, but the brightness equals the size times the reflectivity, and you do not know either one of those by itself. If you assume the object is bright and shiny, you conclude it must be small, because a small shiny thing can account for all that light. If you assume the object is dark, you are forced to conclude it must be large, because only a big dark thing could bounce back that much light while drinking in most of it. Same dot, same brightness. Two completely different objects depending on an assumption you cannot check from the brightness alone. This is the exact corner that 1997 NC1 has backed us into. We can measure its brightness perfectly well. That has never been the issue. The issue is that to turn that brightness into a size, you have to know how reflective its surface is, and that is precisely the thing we have not been able to nail down. And every guess we make about its reflectivity throws the size estimate wildly in a different direction. Guess it is shiny, and it shrinks. Guess it is dark, and it swells. The asteroid sits there, the same physical object it has always been, while our picture of it balloons and collapses depending on which assumption we feed into the equation. It helps to understand how we found this thing in the first place, because the method itself explains a lot about why we know so little. Back in the summer of 1997, this object turned up the way almost all of them do, in a survey, one of those patient automated programs that photograph the same patches of sky over and over, night after night, and then compare the images looking for anything that has moved. The stars stay put. They are so far away that across a human lifetime they do not visibly shift. But an asteroid, close and quick, slides a little against that fixed backdrop from one exposure to the next, and software trained to notice that slide flags it, and a new point of light gets a provisional name and a place in the catalogue. That is the entire act of discovery. Not a close-up, not a portrait. Just the detection of motion, a dot that refuses to sit still among the stars, and once you have caught that motion across several nights, you can do something genuinely powerful with it, which is to work out the orbit. By watching exactly how the dot moves, how it curves, how its speed against the background changes, astronomers can reconstruct the whole ellipse of its path around the Sun, and they can do it with remarkable precision, often within days of discovery. This is why we can say with such confidence that 1997 NC1 will miss us by 2.5 million kilometers, and why we can project its position decades out, and why we can state that this is its closest pass since the 1600s. The orbit, the where it goes, we have nailed. It is everything else, the what it is, that has stayed maddeningly out of reach. We know this object's address and its schedule down to the minute. We just do not know its face. Part of the reason comes down to how faint these things are, and the scale we use to talk about that faintness is worth a moment, because it is deeply unintuitive. Astronomers measure brightness in magnitudes, and the scale runs backward from what you would expect. Smaller numbers mean brighter objects, larger numbers mean fainter ones, and each step of one magnitude is a jump of about 2.5 times in brightness. The faintest stars you can see with your unaided eye on a dark night sit around the magnitude 6. This asteroid, even at its brightest during this exceptionally close pass, will only reach about magnitude 10, which is more than 10 times fainter than anything your eye can detect on its own. And for most of the nearly 30 years we have tracked it, it has been vastly fainter even than that, a speck so dim that only large telescopes could catch it at all, hauling in its trickle of reflected light photon by photon. When the thing you're studying is that faint, every measurement is a struggle, and the margin for error in everything you derive from it is wide. The dimness is not a minor inconvenience. It is a large part of why the mystery has lasted as long as it has. Now, you might reasonably ask, surely there is a way around this. Surely we have a trick to measure the size directly, instead of guessing the reflectivity. And there is. There is a clever one. Instead of looking at the visible sunlight the asteroid reflects, you can look at the heat it radiates. Every object warmed by the sun glows in infrared light, in the same way a stone that has sat in the sun all day radiates warmth after dark, and the amount of heat it gives off depends mainly on its actual surface area, not on how shiny it is. A big object radiates more heat than a small one, almost regardless of colour. So if you can measure that infrared glow, you can in principle get at the true size and then work backward to figure out the reflectivity instead of the other way around. That is exactly what astronomers tried to do with this object back in 2010, using a space telescope built to see in the infrared. And here is where the story takes its first genuinely strange turn, because the answer that measurement gave us did not calm the waters. It made them choppier. The infrared reading suggested this asteroid might be small, possibly as small as 400 meters across. But for an object only 400 meters wide to be as bright as we see it in visible light, its surface would have to be reflecting an astonishing amount of the sunlight hitting it. When you run the numbers, you find that a 400-meter version of this asteroid would need to be reflecting something like 58% of the light that touches it. More than half. And that, for a lump of ancient rock drifting through space, is not just unusual, it is almost unbelievable. Because remember the scale we are working with. A typical dark asteroid reflects a few percent of the light hitting it. A typical stony asteroid might reflect somewhere in the range of 15 to 30%. 58% is the reflectivity of fresh ice, of bright, clean snow, of polished material. It is wildly, almost impossibly high for the surface of an asteroid that has been weathered by the raw radiation of space for billions of years. So now we have a real puzzle on our hands, and it is sharper than just not knowing the size. We have one method whispering that this thing is small, and the only way to make that small size agree with how bright it looks is to accept that its surface is shining backlight like a mirror, in a way that almost nothing in the natural asteroid population does. Either this is a small object with a surface so reflective it borders on the bizarre, or the small size reading is wrong, and this is a larger, darker object that simply looks bright, because there is a lot of it. And that right there is the fork in the road that has split this asteroid's identity in two for the better part of 15 years. Hold that 58% number in your mind, because it is going to come back, and it is going to come back in a context you're not expecting. For now, just sit with the strangeness of it. We are looking at an object that, taken at face value, is either improbably small and improbably shiny, or considerably larger than that and hiding it well. The light cannot tell us which. So to break the deadlock, astronomers turn to a different tool, one that does not just measure how much light the asteroid reflects, but reads the light itself, splits it apart, and tries to pull the chemical fingerprint of the surface straight out of the glow. And when they did that, they did not get one answer, they got three, and the three answers could not all be true. Part 3. 3 asteroids. In one. The tool that was supposed to end the argument is called spectroscopy, and the idea behind it is genuinely beautiful. When sunlight reflects off the surface of an asteroid, the minerals in that surface do not bounce back every colour equally. Some materials drink in red light and throw back blue. Some swallow a particular sliver of the infrared and reflect the rest. Iron-bearing minerals leave one kind of dark band in the reflected light. Carbon-bearing materials leave another. So if you take that single point of light, and, instead of just measuring how bright it is, spread it out into a full rainbow, and study which colours are missing and which are strong, you are effectively reading a chemical fingerprint. You are letting the asteroid tell you, in the language of light, what its skin is made of. Astronomers call this barcode a spectrum, and from it they sort asteroids into types, families of objects that share a chemical character. That should have settled everything. You read the barcode, you learn the composition tells you the likely reflectivity, the reflectivity unlocks the size, and the case is closed. Except that when different teams pointed their instruments at 1997 NC1 over the years and read its barcode, they did not come back with the same answer. They came back with 3 different answers, and the 3 answers describe 3 fundamentally different kinds of object, with 3 different reflectivities, and therefore 3 different sizes. This is the core of the identity crisis, and I want to walk you through all 3, because each one paints a different portrait of the thing that is about to pass us, and you should understand what is genuinely on the table. The first reading, from some of the earlier spectral work, classified this object as what astronomers call a B-type asteroid. B-types are some of the oldest, most primitive objects in the solar system. They are carbon-heavy. They are dark, often extremely dark, the colour of charcoal or printer toner, and they are thought to be relatively unchanged leftovers from the very birth of the planets, material that never got cooked into a world. If 1997 NC1 is a B-type, then it has a low reflectivity, and remember what low reflectivity does to the size estimate. It inflates it. A dark object has to be large to throw back the amount of light we see. So under the B-type reading, this is not a modest object at all. It is pushed toward the very top of the size range, towards something on the order of 1.5 kilometers across. A dark, ancient carbon-black mountain, nearly 1.5 miles wide, drifting in from the early days of the solar system. That is portrait number 1. The second reading came later, and it told a different story. This analysis argued that the object is actually an S-type asteroid. S-types are stony. They are made of silicate rock laced with nickel and iron, and crucially they are considerably more reflective than the dark carbon bodies. They throw back more light. And if this object is more reflective, then it does not need to be as large to account for its brightness, because a shinier surface does more with less. So under the S-type reading, the asteroid shrinks. The estimate comes down to something closer to 900 meters. Still enormous. Still firmly in the range that would matter a great deal if it were ever on a collision course, which, again, this one is not. But 900 meters of stony rock is a very different object from 1.5 kilometers of black carbon. Different origin, different structure, different density, different history. That is portrait number 2, and it cannot be reconciled with portrait 1. They are not two descriptions of the same thing. They are two different things. And then came the third reading, the most recent, and in some ways the most intriguing because it threw a genuine curveball. The newest observations have suggested that 1997 NC1 might be a Q-type asteroid. Now, Q-types are rare, and they are strange in a specific and revealing way. Their spectra resemble the most common kind of meteorite that falls to Earth, the ordinary chondrites, the stony meteorites that make up the bulk of what lands in our deserts and our fields. But here is the puzzle that has long surrounded Q-types. When we look at the broad population of asteroids, we see very few of them with this fresh, chondrite-like signature, even though chondrites are what most of them are made of underneath. The reason is space weathering. Out in the open, an asteroid's surface is slowly bombarded by the solar wind and by micrometeorites, and over millions of years that bombardment darkens and reddens the surface, builds up a kind of cosmic tan, and hides the fresh rock beneath. So a Q-type, with its fresh, untanned, chondrite-like face, is an oddity. It looks young. It looks like something whose surface has, somehow, recently been exposed or renewed. Do you see what that does to the story? If this object is a Q-type, the question stops being only how big it is, and becomes how it has stayed so fresh. Something has to keep wiping that surface clean, or the object has to have arrived in its current state relatively recently. And one of the leading ideas for what refreshes an asteroid's surface is exactly the kind of thing that is about to happen on June 27th. When an asteroid makes a close pass by a planet, the planet's gravity tugs and shears at it, and on a loosely bound body that shaking can cause the surface to shift and slump, turning over buried material and exposing fresh rock to the sunlight. In other words, the very encounters that bring an object close enough for us to study it may also be the encounters that keep resetting its face. The act of coming close enough to be measured might be part of why it looks the way it does. To really feel the weight of that third possibility, you have to understand the strange relationship between asteroids and the rocks that fall on us. Almost every meteorite that has ever been picked up off the ground, the stones in museum cases, the irons that farmers have ploughed up for centuries, came from an asteroid, knocked loose in some collision, and eventually swept up by the Earth. And the most common kind of all, by a wide margin, is the ordinary chondrite, a stony meteorite full of tiny round mineral droplets that froze out of the cloud of gas and dust from which the whole solar system formed. These are, in a real sense, pieces of the original material, barely changed in 4.5 billion years. So when astronomers say a Q-type asteroid looks like an ordinary chondrite, they are saying its surface looks like the fresh, unweathered interior of the solar system's most common building material, as if it had been broken open yesterday. And that is the puzzle. because out in space nothing stays fresh. The moment a surface is exposed, it begins to weather. The solar wind, a thin constant stream of charged particles blowing off the sun, sandblasts it at the atomic level. Tiny micrometeorites, specks of dust moving at enormous speeds, pepper it and melt microscopic glassy splatters across it. Over millions of years, this slow bombardment darkens the surface and reddens its colour, building up that cosmic tan I mentioned, hiding the bright, fresh rock beneath a dull, aged skin. This is why most stony asteroids do not look like the fresh chondrites they are made of. Their faces have been weathered. So a Q-type, looking young and unweathered, is a genuine oddity that demands an explanation. Either it was very recently broken off a larger parent body, exposing fresh rock, or something keeps wiping its surface clean faster than the weathering can age it. And there is one more layer to the composition question that matters enormously for what this object actually is, which is its internal structure. We used to imagine asteroids as solid lumps of rock, single coherent boulders. But everything we have learned in recent decades from the ones we have visited up close tells a different story. Many of them, perhaps most of the larger ones, are not solid at all. They are rubble piles, loose aggregates of boulders and gravel and dust held together by nothing but their own feeble gravity and a little friction with huge empty gaps between the pieces. Such an object can be far less dense than solid rock, sometimes nearly half-empty space inside, and that internal structure changes everything about how it would behave, whether it could be deflected, how it responds to a close pass by a planet, even whether the gentle shaking of an encounter like this week's could cause its surface to shift and refresh. So when we argue about whether 1997 NC1 is a B-type or an S-type or a Q-type, we are not just arguing about colour. We are arguing about whether it is solid or loose, ancient or fresh, a single stone or a flying pile of rubble, and we genuinely do not know which. There is also a quieter reason the readings may disagree that has nothing to do with the object being exotic, and it is worth naming so we do not over-dramatize the puzzle. An asteroid is not a fixed laboratory sample we can hold still under good light. It is a tumbling body seen from constantly changing angles, lit by the sun from different directions on different nights, observed through our shifting atmosphere at the very limit of what our instruments can detect. A surface that is genuinely patchy, darker in some regions and brighter in others, fresher on one face and more weathered on another, can hand you a different spectrum depending on which side happened to be turned toward you when you looked. So some of the disagreement may simply be that different teams caught different faces of the same complicated object at different moments, and each measured a true thing about the piece they saw. That possibility does not resolve the mystery so much as deepen it, because it would mean the object is not one simple type at all, but a mottled, mixed body that genuinely wears more than one face, and only a close, sustained look, the kind the coming days will provide, can stitch those faces into a single whole. So now line them up. One careful reading says dark carbon, 1.5 miles wide. Another careful reading says stony rock, 900 meters. A third careful reading says fresh chondrite, a surface that looks strangely young. These are not small disagreements at the edges of a measurement. These are 3 different asteroids, and the people making these classifications are not careless. They are skilled, they are using real data, and they keep arriving at incompatible answers. That, all by itself, is a clue. When good observers using good methods cannot agree on what something is, it usually means one of 2 things. Either the object is being observed under conditions that keep changing, so that it genuinely looks different at different times, or the object itself is somehow unusual, mixed, or hard to categorize in a way that breaks our normal boxes. Neither possibility is boring, and this is where I have to pull us back to the thread, because it is easy to get lost in the taxonomy and forget the stakes. We have an object that has been catalogued for almost 30 years, that has been formally labelled hazardous, that is about to make its closest pass in 4 centuries, and we cannot tell you whether it is dark or bright, large or merely large, ancient or strangely fresh. The single point of light has refused to resolve into one clear picture. It flickers between identities depending on who is looking and how. And the unsettling truth underneath all of this is that for most of the objects in the sky that could one day matter to us, this fuzziness is not the exception. It is the normal state of our knowledge. We are surrounded by points of light we have only half identified. So before we get to the moment of resolution, before that radar beam reaches out and forces this object to finally hold still and be measured, I think we owe it to ourselves to ask the harder question that all of this is circling. Why does it matter so much exactly how big this rock is? What is the real difference between a 400-metre object and a 1.5-kilometre one, beyond a number on a chart? The answer is that those two numbers sit on opposite sides of one of the most important lines in all of planetary science. One of them is a regional catastrophe, the other is the kind of object that has, more than once in the history of this planet, changed everything that lives on it. And to understand why that line matters, we have to talk about what an object like this would actually do. Part 4. The size class that ends worlds. I want to be very careful here, because I have promised you twice already that this asteroid is not going to hit us, and that remains absolutely true, and I'm going to keep it true every time the subject comes up. 1997, end C1 is going to miss us by 2.6 million kilometres, and there is no scenario on this pass in which that changes. But to understand why astronomers care so intensely about pinning down the size of an object like this, you have to understand what the size means. Because size with an asteroid is not a vanity measurement. Size is destiny. The width of one of these objects determines, more than almost anything else, what it would be capable of doing, and the difference a few hundred meters makes is the difference between a bad day for one region and a bad century for the entire species. Let me build it from the bottom up, because the scale of these things does not work the way intuition expects. Start small. In the year 1908, an object came down over a remote part of Siberia, near a river called the Tunguska. It never even reached the ground. It exploded in the air several kilometers up in a burst of energy that we now estimate at something in the range of 10 to 15 million tons of high explosive. That airburst flattened the forest beneath it across an area of roughly 2,000 square kilometers. 80 million trees snapped and laid flat in a great radial pattern, pointing away from the blast, like matchsticks swept down by a hand. The object that did that is thought to have been only about 50 or 60 meters across. 50 meters. Smaller than the smallest estimate anyone has ever floated for the asteroid passing us this week. An object a fraction the size of 1997, NC1's smallest possible width, levelled a forest the size of a major metropolitan area. And if it had arrived a few hours later, with the Earth turned a little further on its axis, it could have erased a city instead. Now climb the ladder. In 2013, over the Russian city of Chelyabinsk, a smaller object, only about 20 meters across, exploded in the morning sky with the energy of around 500,000 tons of explosive. It broke windows across 6 cities. It injured around 1,500 people, mostly from flying glass as they rushed to their windows to see the brilliant streak of light. And that was 20 meters. The point I am driving at is that these objects scale viciously. The energy does not climb gently as the object gets bigger. It climbs in great leaps, because the energy depends not just on the size but on the mass, and the mass climbs with the cube of the width. Double the width, and you do not double the punch. You multiply it roughly 8-fold. So as you move up from a 20-meter Chelyabinsk to a 50-meter Tunguska, to a 100-meter object to a 500-meter object, you are not walking up a gentle slope. You are taking the elevator up the side of a cliff. So now carry that all the way up to the object we are actually talking about. Carry it up to a body somewhere between 400 meters and 1.5 kilometers across. At those sizes, you have left the world of regional disasters entirely. An object even at the lower end of that range hitting the planet would release energy measured not in millions of tons of explosive but in tens of thousands of millions of tons, in numbers that stop meaning anything to the human mind because we have no experience to anchor them to. It would carve a crater many kilometers wide. If it came down in the ocean, which most objects would, simply because most of the planet is ocean, it could raise waves on a scale that coastlines have not faced in recorded history. But the crater and the waves are not even the worst of it. The worst of it is what happens to the sky. When an object of around a kilometre or more strikes the Earth, it throws an enormous quantity of pulverised rock and dust high into the atmosphere, so high and in such quantity that it spreads around the entire planet and hangs there. That veil of debris dims the sun, and when you dim the sun across the whole Earth for months or years, you cool the surface, you interrupt the seasons, and most catastrophically, you interrupt the ability of plants to grow. Crops fail, not in one country, but everywhere at once. The food web, which rests entirely on sunlight reaching green leaves, begins to come apart from the bottom. This is the scenario that planetary scientists have in mind when they talk about the threshold of global catastrophe, and they generally place the onset of that planet-wide effect right around the 1 kilometre mark. That is the line. Below it, even a severe impact tends to be survivable as a civilization, however horrific it would be locally. Above it, you are talking about the kind of event that does not just kill people, but threatens the entire structure of life as we have organized it. And we know this is not theoretical, because it has happened. Around 66 million years ago, an object thought to be something like 10 kilometers across struck what is now the coast of Mexico, near a place we now call Chicxulub. That single object ended the age of the dinosaurs. It did not do it by crushing them under the impact. It did it by what came after, the global darkness, the collapse of plant life, the unraveling of the food chain, the long cold. Roughly 3/4 of all the species alive on Earth were gone when it was over. The point is not that 1997 NC1 is a Chicxulub object. It is not. It is much smaller, and again, it is not going to hit us. The point is that the line exists, that it is real, that this planet has crossed it before with catastrophic results, and that the object passing us this week sits in the size range where, if its orbit were different, the question of which side of that line it falls on would be the only question that mattered. This is why the size argument is not academic. When researchers fight over whether this object is 400 meters or 1.5 kilometers, they are in a sense fighting over which category of threat the object's whole class represents, and over how well we actually understand the population of large bodies in our neighborhood. And here is the thread again, tightening, because this object is the one we have been watching for 30 years, the one we caught early, the one we flagged and named and tracked, and we still cannot say for certain which side of the catastrophe line its size would put it on. We got everything right. We found it, we followed it, we labelled it, and we still do not know its size to within a factor that for any object actually on a collision course would be the single most important number in human history. It is worth slowing down on what an impact of this size would actually look like, not to frighten you about an event that is not happening, but because the specifics are the only way to truly grasp why that 1 kilometre line is drawn where it is. Consider first that most of the Earth is water, so the single most likely place for any large object to come down is the open ocean. People sometimes imagine that an ocean impact would be gentler, that the water would somehow cushion the blow. The opposite is closer to the truth. A kilometre-scale object hitting the open ocean would punch straight through the water column as if it were barely there, blast a transient crater in the seafloor, and hurl an unimaginable volume of water upward and outward. The waves radiating from that wound would not be ordinary waves. They would move outward across the basin and reach distant coastlines hours later, as walls of water, scouring low-lying shores around an entire ocean rim, the very coastlines where most of humanity has chosen to build its great cities. But as I said before, the waves and the crater are local compared to what happens to the air and the light. When an object that large hits, whether on land or sea, it converts an almost incomprehensible amount of kinetic energy into heat and force in an instant. The energy released by a 1 kilometre impact would dwarf the combined yield of every nuclear weapon ever built, not by a little, but by a wide margin, all of it delivered in a single point in a single moment. That blast lofts pulverized rock and soot and water vapour high above the weather, into the upper atmosphere where there is no rain to wash it out, and there it spreads, carried by the high winds, until it wraps the entire planet in a dimming veil. And once the sky dims worldwide, the chain of consequences runs downhill with terrible logic. Less sunlight reaches the surface, temperatures fall, the growing season collapses, not in one place but globally and at once. The plants that feed everything fail, and the failure climbs the food chain from the bottom up. That is precisely the mechanism that ended the age of the dinosaurs, and it is worth being concrete about how it unfolded, because it is the closest thing we have to a full rehearsal of the worst case. When the 10-kilometre object struck near what is now Mexico 66 million years ago, the immediate devastation was regional, ferocious, but regional. What made it a global extinction was the aftermath. The months and years of darkened skies and collapsed plant life and broken food webs that followed. photosynthesis faltered across the whole planet. The great reptiles that had ruled the land and the sea for over 150 million years could not survive a world where the bottom of the food chain had given way, and roughly 3 out of every 4 species then alive vanished from the record. The object did not have to kill them directly. It only had to dim the sun long enough, and the rest followed on its own. That is what the 1 kilometre threshold is really measuring. It is the size at which a single object stops being a disaster and starts being a global reset. Which raises the question that I think is the genuinely frightening one, and it is not about this rock, because this rock is going to miss. It is about the rocks we did not catch early. It is about the ones we have not found at all, because if the system worked perfectly on this object and still left us this uncertain, then what about the objects the system has not gotten to yet? How many are there? How big might they be? And is there any direction in the sky where our watchfulness simply does not reach? A blind spot we cannot close, where something the size of a catastrophe could be sitting right now, hidden, waiting, and we would not know until it was almost on top of us. As it turns out, there is exactly such a direction, and we look straight into it every single morning. Part 5. The Asteroids That Come from the Sun. Here is something that almost nobody outside of astronomy realizes about how we hunt for these objects, and once you understand it, you will never look at a sunrise quite the same way again. We find asteroids with telescopes, and telescopes, for the most part, work at night. They work by catching the faint reflected glow of an object against a dark sky, and that means there is one direction in the entire sky into which our ground-based telescopes are essentially blind, and that direction is the direction of the sun. Any object that approaches the Earth from the sunward side, coming at us out of the glare, is hidden in exactly the same way a car is hidden when it drives toward you out of a low, blinding sunrise. The light that should reveal it is the very thing that erases it. We call these objects, when we eventually do find them, twilight asteroids, because the only time we have any hope of catching them is in those brief, narrow windows just after sunset or just before dawn, when the sky is dark enough to see but our line of sight still skims close to where the sun sits below the horizon. It is a tiny, grudging window, and most of the time it is not enough. An object can ride in on the daytime side of the sky completely invisible, growing closer and closer, and we will not see it until it crosses over into the night side, by which point, if it were on a collision course, it could be far too late to do anything but watch. And this is not a hypothetical weakness. We have been blindsided by it. The Chelyabinsk object, the one that exploded over Russia in 2013 and injured around 1,500 people, came at us from the direction of the sun. Nobody saw it coming. Not one telescope, not one observatory, not one of the systems we have built to watch the sky caught it before it arrived, because it was hiding in the one place we cannot look. The first warning anyone on Earth had was the flash itself, the sudden second sun blooming in the morning sky over the city. We did not detect it. We experienced it, and it was only 20 meters across. Now hold that fact next to everything we have just been discussing about the size class of the object passing us this week, and you will understand why this blind spot keeps planetary defense specialists up at night. So you might reasonably ask, if we know about this blind spot, why have we not fixed it? And the answer is that fixing it is genuinely hard, because the problem is not a lack of cleverness. It is a law of physics about where you can stand. To see objects coming from the direction of the sun, you cannot stand on the night side of the Earth and look toward the daytime sky, because the atmosphere lit up by the sun drowns everything out. You have to get above the atmosphere entirely, out into space. And ideally you have to position your telescope not near the Earth at all, but somewhere closer in toward the sun, looking outward, so that the region of sky that is dangerous to us is in front of you and dark, rather than behind the glare. And you cannot do it with an ordinary telescope that hunts for reflected light. You have to build a telescope that hunts for heat, for the infrared glow these objects give off, because in the infrared an asteroid stands out against the cold of space even when it is washed out in visible light. That is exactly the kind of instrument that is now being prepared, a dedicated infrared asteroid hunting space telescope designed to take up a position sunward of the Earth and finally watch the blind spot from the inside. It is the fix we have needed for decades, but it is not flying yet. It is still being readied for launch, still in the long pipeline that turns an idea into hardware sitting in the dark a million miles from home. And until it is up there and working, the blind spot remains open. Every morning the sun rises, and behind it, in a region of the sky we cannot search, the population of objects we have not yet found goes about its business unseen. When that infrared hunter finally reaches its post and opens its eyes, it will change this part of the story in a way that is hard to overstate. From a vantage point in toward the sun, looking outward, it will be able to sweep the very region of sky that has always been lost to us in the glare, the daytime approach lane, and it will see the objects there not by their faint reflected light but by the heat they carry, which stands out cleanly against the cold of space. In a matter of years of operation, it is expected to find the large majority of the dangerous objects in the size range we have been most blind to, the regional city killers, including the ones that have been hiding sunward of us all along. It is, in effect, the closing of a door that has stood open since the beginning, the single biggest upgrade to our ability to see what is coming that our species has ever attempted. The frustrating part is only that it is not finished yet, that for now the door remains open and the glare remains unsearched, and that an object arriving from that direction this year or next would still catch us the way the one over that Russian city did. We can see the fix coming. We are just not standing behind it yet. Now, I want to be fair and precise here, because the channel does not deal in panic, it deals in what is actually true, and the truth has a reassuring half as well as a frightening one. For the very largest objects, the genuine civilization enders, the ones a kilometre and up, we have actually done quite well. Decades ago, the people responsible for this took on a mandate to find the great majority of the kilometre-class objects near Earth, and they have largely succeeded. The best estimates are that we have now found something on the order of 95% of the asteroids in that largest, most dangerous size class. That is a real achievement, and it deserves to be said plainly. The odds that there is an undiscovered, untracked, civilization-ending mountain out there with our name on it are genuinely low, lower than they have ever been in human history because of patient work done by people who will never get the credit. But notice the gap that careful sentence leaves open. 95% is not 100%. It means that even among the very largest objects, a small fraction remain uncatalogued, and a small fraction of a very large and very consequential population is not nothing. And once you step down even slightly in size, into the range that could still erase a city or devastate a region without quite ending the world, our completeness falls off a cliff. There, we have found only a fraction of what is out there, and in the sunward blind spot across all sizes, our knowledge thins out into something close to a guess. So the honest picture is this. The thing most likely to end civilization, we have probably already found and are probably already tracking. But the thing that could still kill a great many people, arriving from a direction we cannot watch, in a size class we have only partly mapped, remains a live and open question. And the object passing us this week is the perfect, uncomfortable illustration of why. Because even for the ones we have found, our knowledge is so much shakier than people assume. It is worth knowing that this watching, this constant search of the sky, is not some vague background activity, but a real, organised, decades-long effort with a specific origin, because that history is also the story of how the gap got measured in the first place. Toward the end of the last century, it began to dawn on people, scientists first, and then governments, that the dinosaurs had been wiped out by exactly this kind of object, and that there was no law of nature protecting us from the same fate, and that we were, almost uniquely among the threats we face, capable of seeing this one coming if only we bothered to look. And so a mandate was handed down, a charge to systematically find the large near-Earth objects, first the genuine giants, the kilometre-class civilization enders, and later, with a tightened mandate, the great population of smaller but still city-destroying bodies down to a much smaller size. The goal was to find the overwhelming majority of them, to build, for the first time in the history of life on Earth, an actual inventory of the things that could end us, and a set of dedicated survey programs has been chipping away at that mandate ever since. Automated telescopes that sweep the same broad swaths of sky night after night, hunting for those telltale moving dots. They are the reason the catalogue of known near-Earth objects has grown from a few hundred to many tens of thousands within living memory. They are why we can now state, with real numbers behind it, that we have found something like 95% of the largest, most dangerous class. That figure did not come from nowhere. It came from years of patient, unglamorous sweeping of the dark by machines and the people who run them, and from the careful statistical work of estimating how many objects must still be out there based on how often the surveys rediscover ones they already know versus stumble on genuinely new ones. The completeness estimate is itself a hard-won scientific achievement, but the same careful accounting that lets us say we have found most of the giants also tells us, in the same breath, exactly where we fall short, and the fall-off is steep. Step down from the 1-kilometre giants to the objects a few hundred metres across, the ones that could obliterate a region or raise an ocean-crossing wave without quite ending the world, and our completeness drops sharply to well under half of the estimated population. Step down again to the size of the object that burst over that Russian city, the city window-shattering size, and we have found only a tiny sliver of what must be out there, a few % at most. The surveys have done extraordinary work at the top of the size range and are still nearly blind across the bottom of it. So the reassuring headline, that the true world enders are mostly mapped, sits right alongside the uncomfortable fine print, that the far more numerous merely catastrophic objects are mostly still unknown, and that all of this assumes the object obligingly approaches from the night side, rather than out of the glare we cannot search at all. And there is one more limit, subtler than the blind spot, but in some ways even more humbling, because it is not about where we can look, it is about how far into the future we can actually see, even for the objects we are watching perfectly. Because it turns out that knowing exactly where an asteroid is today does not mean you know where it will be in a few hundred years. In fact, there is a hard wall in our ability to predict these orbits, a horizon beyond which even our best mathematics dissolves into a fog of uncertainty, and that wall is closer than you would ever guess. To understand why it is there, and why this week's radar measurements are partly a way of pushing that wall back, you have to understand a force so faint that for most of the history of astronomy we did not even know it existed, a force made of nothing but sunlight and heat that over centuries can shove a mountain off its course. Part 6. The 100-Year Wall. There is a comforting idea most of us carry around about the solar system, and it goes like this. The planets and the asteroids move according to gravity. Gravity is a clean and exact law. We have known it since Newton, and therefore the motion of these objects is perfectly predictable. Wind the clock forward, and the mathematics will tell you precisely where everything will be, a year from now, 1,000 years from now, 1,000,000. It is a beautiful idea, and for the planets, over human timescales, it is more or less true. But for a small object like an asteroid, it quietly breaks down, and it breaks down sooner than almost anyone expects. We can confidently predict the path of a well-tracked near-Earth asteroid for roughly 100 years. Beyond that, the predictions begin to come apart, and not because our mathematics is sloppy, but because reality includes forces that are almost impossible to pin down in advance. The most important of those forces has a name that sounds like it belongs in a spy novel. It is called the Yarkovsky effect, and it is one of the most elegant, sneaky pieces of physics in the whole solar system. Here is how it works. An asteroid sits in sunlight. The side facing the sun warms up, the way the sunlit side of your face warms up on a clear day. But the asteroid is also spinning, so as it turns, the warm patch of surface rotates around toward the evening side, and there, in the cool of its own afternoon, it radiates that stored heat back out into space. Now, here is the subtle part. When that warm surface gives off heat, the heat leaves as infrared radiation, and radiation, faint as it is, carries a tiny push. Light pushes on things, so the asteroid is in effect gently breathing out heat in a preferred direction, and that breath acts like an impossibly small rocket thruster, nudging the object ever so slightly, continuously for millions of years. Any single moment of that push is laughably tiny. It is nothing. It would not move a feather on a table, but it never stops. It acts every second of every year across the entire surface of the object, and over centuries and millennia those infinitesimal nudges accumulate into a genuine change in the orbit. An asteroid subject to the Yarkovsky effect can drift, over long enough time, a meaningful distance away from where pure gravity alone would have placed it. And here is the killer detail, the thing that turns this from a curiosity into a wall in our knowledge. The strength and even the direction of that push depend on things about the asteroid that we usually do not know. It depends on how the object spins, on which way its axis points, on how quickly its surface absorbs and releases heat, on its exact shape, on whether its surface is loose dust or solid rock. Get any of those wrong, and you get the push wrong. And if you get the push wrong, then every year your prediction drifts a little further from the truth, until, after about a century, the error has grown so large that you can no longer say with confidence exactly where the object will be. This is the 100-year wall. It is not a limit on our telescopes. It is a limit baked into the physics of small bodies being gently shoved by their own warmth, combined with the fact that every close pass an asteroid makes by a planet bends its path and resets the uncertainty all over again. Each time one of these objects swings near a world, the planet's gravity grabs it, redirects it, and amplifies whatever tiny uncertainties were already there. The way a single nudge to a billiard ball becomes a completely different table after a few more bounces. So the further out you try to predict, the more these effects compound, until the single clean line of the orbit you started with has blossomed into a widening cloud of possibility, a smear of places the object might be, rather than a point where it will be. For a long time, the Joukowsky effect was purely theoretical, a clever idea proposed more than a century ago by an engineer working in his spare time, too small to measure and easy to dismiss. It sat in the background of celestial mechanics for generations, acknowledged but unproven, because how could you ever detect a push that gentle acting on a mountain in space? And then, using exactly the kind of radar we're going to use on this object, astronomers managed to catch it in the act. They tracked a particular small asteroid across multiple close passes, measured its position with radar precision, and found that it had drifted from where pure gravity said it should be, by a distance that could only be explained by that faint thermal thrust quietly pushing on it year after year. The ghost force was real. It had been moving asteroids the whole time, and we had finally measured its fingerprints. That confirmation transformed the Joukowsky effect from a curiosity into something every serious orbit prediction now has to account for, and it is why measuring this object precisely this week is so valuable. And there is a reason the long-term uncertainty matters so much more than it might first appear, and it has to do with something planetary defense specialists call a keyhole. A keyhole is a tiny region of space, sometimes only a few kilometers wide, that an asteroid might pass through on one encounter, and the thing that makes it dangerous is what it does to the next encounter. If an object threads exactly through one of these keyholes, the planet's gravity bends its path by just the right amount to set it up for an impact or a much closer pass years or decades later. So the question of whether a future approach is harmless or catastrophic can come down to whether the object passes through a region of space smaller than a city on a pass that might be many years away. And whether it hits that keyhole depends on the very things we have been talking about, on the precise orbit, on the accumulated Joukowsky drift, on the exact geometry of every encounter in between. This is why a small uncertainty today can blossom into the difference between safe and not safe far down the line, and why pinning the orbit down with radar, shrinking that cloud of possibility, is not academic bookkeeping. It is quite literally how you find out years in advance whether a keyhole is even in play. None of this, I want to stress again, applies to 1997 NC1 as a threat. Its orbit is well enough known that we are confident in this pass and in the passes we can currently project, and it is not threading any keyhole toward us. But the principle is exactly why this object is such a perfect teacher. It shows you, in a completely safe example, the whole machinery of how we track these things and where that tracking reaches its limits. Every precise measurement we take this week of this harmless object sharpens the very tools and the very understanding we would need if a future object were not harmless. In a sense, this flyby is a free lesson, a chance to practice reading the future of an object's orbit on one that cannot hurt us, so that we are better at it for one that someday might. And now you can see why this week matters for reasons that go beyond solving the size and composition mystery. Because when that radar beam reaches out and touches 1997 NC1 on June 27th, it does not just measure how wide the object is. It measures, with extraordinary precision, exactly how far away it is and exactly how fast it is moving toward or away from us, far more precisely than any optical telescope watching a point of light ever could. And those precise measurements get fed back into the equations that describe the orbit, and they tighten that orbit dramatically. They take the widening cloud of future possibility and they shrink it back down toward a line. In a very real sense, every radar contact with one of these objects buys us time. It pushes the 100-year wall a little further into the future, sharpens our knowledge of where this thing will be, not just on its next pass, but on passes, long after everyone watching this is gone. That is the quiet, beautiful thing about what is going to happen this week. Underneath all the talk of danger and mystery, we're not just going to solve an old argument about what this rock is. We're going to take a faint, ambiguous, drifting object whose future we could only predict so far, and we're going to nail it down, refine its path, and extend the reach of our own foresight. We're going to know it better in every dimension than we ever have, and we will have done it by reaching across 2.5 million kilometers of empty space and listening for a return. But I have been talking about this object as though everyone agrees it is just a rock, an ordinary if poorly measured lump of natural material, and for the overwhelming majority of scientists that is exactly what it is. But you and I both know that an object this strange, this hard to classify, this resistant to 30 years of careful measurement, was never going to be left alone as just a rock. Because that impossible brightness, that 58% reflectivity I asked you to hold on to earlier, has a second life. To most researchers, it is a measurement puzzle, but to a smaller and louder set of voices, it is something else entirely. It is a clue, and the conclusion they draw from it is one that mainstream science will not touch, but that I think we have to look at honestly, if only to understand exactly where it goes wrong, and exactly where, uncomfortably, it does not. Part 7. The question. Nobody wants to ask out loud. Let me lay the argument out the way its proponents would as fairly as I can, because I think you deserve to hear the strongest version of it rather than a straw man, and because the only way to take an idea apart honestly is to first build it at its best. The argument goes like this. We have an object that has been tracked for nearly 30 years and that refuses to be classified. Measure it one way, and it looks improbably small and improbably shiny. Measure it another, and it looks like a dark mountain. Read its chemical barcode, and you get 3 incompatible answers, and right at the centre of it sits that one number that should not be there. A surface that, under one reading, reflects 58% of the light that hits it. A reflectivity that belongs to ice and polished metal, not to weathered ancient stone. To most scientists, that number is a sign that something in the measurement chain is off, that the object is bigger and darker than the small reading suggests. But to the proponents of the more exotic view, that number is not an error to be explained away. It is a signal. Because what kind of surface, they ask, reflects light like polished metal? The answer, in our own experience, is polished metal. A smooth, engineered, manufactured surface. A hull. They point out that an object passively scattering sunlight like a dead lump of rock should not be this bright. And they ask whether what we're looking at could be a surface that was made rather than formed. Plating designed to survive the brutal environment of open space. And they take it one step further, into the territory of that faint, mysterious, non-gravitational nudge. We attribute the tiny drift in these orbits to the Yarkovsky effect, to sunlight and heat. But what if, they ask, that subtle push is not waste heat at all? What if it is correction? What if it is the faint signature of something adjusting its own course, and our equations are simply forcing a deliberate motion into the box labelled natural physics, because natural physics is the only box we are willing to open? I want to be honest with you, because that is the whole point of this channel, and the honest thing to say is that this is not a stupid argument. It is built on real anomalies. The classification really is a mess. The brightness really is strange. And we are not without precedent for taking this kind of question seriously, because not very long ago the entire scientific world wrestled with exactly this debate over a different object. In 2017, the first known visitor from beyond our solar system passed through, a strange, elongated object on a path that proved it had come from interstellar space. It tumbled oddly, it brightened in ways that puzzled people, and it appeared to accelerate slightly as it left, with a push that some struggled to fully explain by ordinary outgassing. And a small number of serious credentialed scientists raised the possibility, out loud, in the open literature, that we should at least consider whether it might be artificial, a fragment of technology from somewhere else. They were not cranks. They were asking the question that honest curiosity demands you ask when an object refuses to behave. So I'm not going to stand here and mock anyone for looking at 1997 NC1 and wondering. Wondering is allowed. Wondering is how science starts. But here is where I have to follow the evidence rather than the excitement. because keeping an open mind does not mean letting your brain fall out, and the honest weighing of this particular case comes down firmly, if not entirely comfortably, on the side of nature. Take the brightness first. An implausibly high reflectivity is dramatic, but it has a far more ordinary explanation than an alien hull, and it is the explanation most scientists reach for immediately. The object is simply larger and darker than the smallest estimate assumes, and the apparent 58% reflectivity is an artifact of combining measurements that each carry their own uncertainty. When you let the object be a kilometre-scale dark body instead of a 400-metre mirror, the impossible brightness evaporates. It was never a hull. It was a clue that we had the size wrong. Take the mysterious push next. The trouble with reading the Joukowsky drift as deliberate steering is that the Joukowsky effect is not a fudge factor we invented to hide alien engines. It is a measured, understood, predictable consequence of basic thermal physics that acts on every spinning, sunlit body in the solar system, on rocks we have visited, on rocks we have landed on. A spinning rock that gives off heat experiences this push whether anyone wants it to or not. To see the gentle thermal drift of an asteroid and call it propulsion is to ignore that the same drift shows up, in exactly the predicted way, on objects nobody thinks are spacecraft. And the conflicting spectral types, the third leg of the argument, point to a weathered, possibly mixed natural surface, the kind of complicated face that real asteroids genuinely have, not to manufactured plating, which would, if anything, give a cleaner and more consistent signal, not a messier one. There is a principle that I think is the right compass to navigate all of this by, and it is one that the careful scientists who raise the question about that interstellar visitor would themselves endorse. The principle is that an extraordinary claim requires extraordinary evidence. It is not enough for an object to be merely strange, merely hard to classify, merely surprising, because the universe is full of natural things that are strange and surprising, and our categories are human inventions that nature was never obligated to respect. The bar for concluding that something is artificial, that it was made by a mind rather than shaped by physics, has to be set very high, precisely because the conclusion would be so monumental, and the test is not whether we can rule out the artificial explanation, because you can almost never fully rule anything out. The test is whether the natural explanation has run out of room, whether the ordinary physics genuinely fails to account for what we see. With this object, the ordinary physics has not run out of room at all. It accounts for everything. The strange brightness, the conflicting types, the gentle drift, all of it sits comfortably inside what natural asteroids are known to do. And I think it is worth being honest about why the artificial idea is so seductive anyway, because the pull of it is real and it is human. We are a species that has spent its whole existence looking up and wondering whether we are alone, and every genuinely puzzling object in the sky lands on that ancient nerve. When something refuses to fit our boxes, a part of us leaps, almost hopefully, to the most extraordinary possibility, because that possibility would answer the oldest question we have. I feel that pull myself. I would be lying if I said the idea of pointing a radar dish at a passing object and discovering geometry that should not be there did not quicken something in me. But the discipline of actually wanting to know the truth means holding that hope at arm's length and letting the evidence lead, rather than letting the longing lead and dragging the evidence behind it. The honest position is not to deny that you want it to be something wonderful. It is to admit that you do, and to measure carefully anyway. So here is where I land, and I want to be precise about it. The artificial hypothesis is not crazy. It is just unsupported, and crucially it is about to be tested in the most direct way imaginable. This is the part I find genuinely satisfying. We do not have to argue about it forever. We do not have to choose between belief and disbelief in the dark. Because the very thing that makes this object a mystery, its refusal to be measured from a faint point of light, is about to be overruled. On June 27th, we're going to hit this object with radar, and radar does not care about your hypothesis. If 1997 NC1 is a natural rubble pile of ancient stone, the return will show it, in its lumpy, irregular, cratered, entirely natural shape. And if there were ever genuinely going to be anything anomalous about its structure, anything smooth, anything geometric, anything that did not belong, this is precisely the moment, and precisely the instrument, that would catch it. The open question is not going to stay open. It is going to be answered, on camera, within days. And the overwhelming scientific expectation, which I share, is that what we will see is a natural asteroid, finally measured, finally known. But I will be watching, and so should you. Because the beautiful thing about this kind of mystery is that nature does not get a vote on what we believe. It only gets a vote on what is true, and very soon it is going to cast it. So let us talk about the instrument that is going to cast that vote. Because if the entire problem with this object is that we have only ever seen it as a single, ambiguous point of light, then the solution is to stop relying on light altogether and to reach out across the dark with something else entirely. And in a stretch of high desert in California, there is a machine built to do exactly that. Part 8. The Eye in the Desert. In the Mojave Desert, out past the edges of Los Angeles, there is a field of enormous dish antennas pointed up at the sky, and one of them is among the most remarkable scientific instruments humanity has ever built. It is a giant, a steerable dish 70 meters across, wide enough to cradle a baseball infield, part of the network we use to talk to our spacecraft as they cross the solar system. But this antenna does something else, something that turns it from an ear into a kind of hand. It can transmit. It can hurl a powerful, tightly focused beam of radio energy out into space, aim it at a passing asteroid, and then fall silent and listen for the faint whisper of that beam returning, bounced off the surface of a world millions of kilometers away. That facility is called the Goldstone Solar System Radar, and on June 27th it is one of the instruments that is going to be turned toward 1997 NC1. I want you to appreciate just how different this is from everything we have talked about so far, because it is the whole reason this flyby can solve the mystery, when 30 years of ordinary observation could not. When we look at an asteroid with a normal telescope, we are passive. We are catching whatever sunlight happens to bounce our way, and as we have seen, that light is ambiguous, tangled up with reflectivity, easy to misread. Radar is the opposite. With radar, we are not waiting for nature to send us a hint. We are sending our own signal, a signal whose exact strength and timing and character we control completely, and we are reading what comes back. And because we know precisely what we sent, every single thing that is different about the returning signal is information about the object itself. The way the signal is delayed tells us the distance, down to a stunning precision. The way it is stretched and spread in frequency tells us how fast the object is moving and how fast it is spinning. And the way the beam scatters off different parts of the surface lets us build, piece by piece, an actual map of the thing. This is how radar can take a single point of light and turn it into a world. By carefully analysing how the return arrives, astronomers can construct a three-dimensional model of the asteroid, its true shape, whether it is round or elongated, whether it is a single solid body or two objects stuck together in a contact pair, whether it has ridges, concavities, a neck, a bulge. They can measure the true diameter directly without ever having to guess the reflectivity, which means that the entire size argument, the 400 meters versus 1.5 kilometers argument that has raged for 15 years, simply ends. The radar measures the width. The answer arrives, and from the strength and the polarization of the return, from how the radio waves are twisted as they bounce, they can read the texture and the density of the surface, whether it is smooth or rough, packed or porous, which feeds directly back into the question of what it is made of. In one observing campaign, the radar can settle, or at least dramatically narrow, every single one of the mysteries we have spent this whole video circling. The way radar builds a picture out of a return is so clever that it deserves a moment of its own, because it is not like taking a photograph at all. When that beam washes over the asteroid, different parts of the surface are at slightly different distances from us, and the parts that are nearer send their return back a hair sooner than the parts that are farther away. At the same time, because the asteroid is rotating, one edge of it is turning toward us while the other turns away, and that motion stretches and compresses the returning radio waves by a tiny, measurable amount, the same effect that makes a passing siren change pitch. So every patch of the surface comes back to us tagged with two pieces of information at once: how far away it is and how fast it is moving toward or away from us, and by sorting the return along those two axes, astronomers can reconstruct where every piece of the surface sits. Run that process as the object turns, and the flat return blossoms into a three-dimensional model. We are, in effect, building a sculpture of the asteroid out of the timing and the pitch of a radio return. This technique has already given us our first real portraits of dozens of these objects, and the results rewrote what we thought asteroids were. Radar is how we first saw that some near-Earth asteroids are not single bodies at all, but two lobes joined at a narrow waist, the contact binaries I mentioned, looking for all the world like a cosmic peanut or a snowman. Radar is how we caught others spinning so fast they should be flying apart, and how we measured the loose, rubble-pile nature of still others. Objects that had been nothing but points of light for decades suddenly had shapes, had surfaces, had character, all pulled from the return of a beam. So when this same capability is turned on 1997 NC1, we are not hoping for a vague improvement. We are expecting, based on a long track record, to go from knowing essentially nothing about its shape to holding a detailed model of it in our hands within days. There is a sober footnote to this, though, and it is part of why this particular flyby carries extra weight. For decades, the world had two great planetary radar facilities, and the loss of one of them a few years ago, when a giant dish in the tropics collapsed, left us with far less of this capability than we used to have. The dish in the California desert that will observe this object is now one of the most important planetary radar instruments left standing. That means opportunities like this one, a large, mysterious, potentially hazardous object making an exceptionally close and well-timed pass, are more precious than they were, because we have fewer eyes of this exact kind to spend on them. We cannot afford to waste a pass this good. The window is narrow, the instrument is rare, and the object is exactly the kind we most want to understand. Everything lines up to make these few nights count, and it can do something else. The thing we touched on a moment ago, which is to pin the orbit. Because radar measures the distance and the speed so exactly, far more exactly than tracking a faint dot ever could, a single radar campaign tightens our knowledge of this object's path enormously. It takes that widened cloud of future uncertainty, the one the Yarkovsky effect and the close encounters keep inflating, and it collapses it back down. After this flyby, we will know where 1997 NC1 is going to be, on this orbit and on orbits far in the future, with a confidence we simply did not have before. We will have reached out, touched it once, and in that single touch learned more about it than in the 30 years of watching that came before. Now here is the part I love most and the part I want you to actually do something with, because this is not only a story about giant government antennas and professional scientists, this flyby belongs to you too. Because 1997 NC1, as it makes this exceptionally close pass, is going to brighten in our sky to around 10th magnitude. That is too faint for the naked eye, but it is well within the reach of a modest backyard telescope, and under dark skies, with a good star chart, even a solid pair of binoculars gives you a fighting chance. If you have ever owned a telescope and let it gather dust in a closet, this is the week to pull it out. Because what you would be looking at, that faint moving speck, is the very object we have spent this whole time trying to understand. The 400-year visitor, the thing that has worn 3 different identities, the mystery that radar is about to solve, and you can see it with your own eyes, moving against the stars in real time. If you do want to try to catch it yourself, let me give you the practical shape of it, because this is genuinely doable and I do not want you to miss the chance. The nights around the 27th are your window, when the object is near its closest and therefore near its brightest. You will need a telescope of modest size, or under truly dark skies, a steady pair of binoculars, and you will need a finder chart, which is simply a map showing the object's predicted path against the background stars hour by hour, the kind of chart that observatories and astronomy sites publish for exactly these events. Because the object is moving relatively quickly across the sky, the trick is not to look for a fixed point, but to watch a specific star field over the course of many minutes and catch the one faint dot that has shifted position against all the others. That motion is the giveaway. That slow crawl is the same crawl that betrayed the object to its discoverers nearly 30 years ago, and you can witness it with your own eyes from your own yard. And if the weather fails you, or you do not have a telescope, you're not shut out, because a number of observatories and online observing programs plan to point their instruments at this object and stream the view live as it passes. You will be able to sit at home and watch, in real time, that faint speck drift across the stars with astronomers narrating what they are seeing. There is something quietly moving about that, about the fact that an event like this, which 4 centuries ago no human being on Earth could have known was happening, is now something any of us can pull up and watch from a screen in our own home, as it unfolds. The same object, the same passage, but a species transformed in the time between visits from blind to watching. And this is where the human side of all of this comes into focus, because the watching of the sky has never been only a job for governments. There is an entire community of amateur astronomers and citizen scientists who point their own telescopes at objects exactly like this one, who carefully measure their positions and their brightness night after night, and who report those measurements to the central clearinghouse that tracks every known small body in the solar system, the Minor Planet Center. These ordinary people, working from backyards and rooftops and remote dark sky sites, are a real and genuine part of planetary defense. Every measurement they send in helps refine an orbit, helps confirm a position, helps keep the catalogue of what is out there honest and current. When that radar beam goes out on June 27th, it will be the headline. But around it, quietly, a whole network of human eyes will be tracking the same object, adding their small, precise contributions to the great shared effort of knowing what shares our space. So we are now just days away from the moment of resolution. The instrument is ready, the geometry is right, the object is closing in on the point in its 4-century orbit where it comes nearest to us, and when it does, we are going to measure it at last. But before we get to that final moment, I want to step back and put this single object into a slightly larger frame, because 1997 NC1 is not passing us in isolation. It arrives at a strange time, a time when our attention has already been pulled, again and again, toward the objects crossing our neighbourhood. And just days ago, another giant, another flagged and watched and worried over body, was on all our minds for a very different reason. The two of them, side by side, tell you almost everything about where we actually stand. Part 9. 2 visitors, days apart. If you have been with this channel over the last week or so, you will remember that just a few days ago we sat down and talked at length about another asteroid entirely, one with a far more famous and far more menacing name, the one named for the ancient god of chaos. That object is on its own path toward a genuinely historic close approach a few years from now, one that will bring it shockingly near to us, near enough that we will be able to watch our own planet's gravity reach out and physically work on it, tugging at its structure, possibly changing the way it spins. That was a story about the future, about an encounter still to come, and about an interior we have never been able to see. And now, only a few days later, here we are again, talking about a second large flagged watched object making a close pass. It is worth asking what it means that these two stories are landing on top of each other. It does not mean the sky is suddenly more crowded than usual, or that something has changed, or that we are under some new bombardment. I want to be clear about that because that is exactly the kind of false pattern the mind loves to manufacture. The truth is quieter and, in its way, more interesting. These objects are passing all the time. Close approaches by sizable asteroids are not rare events that cluster meaningfully. They are a constant, steady drumbeat, happening month after month, year after year, mostly unremarked, because most of the time nobody is paying attention. What is unusual is not that two large objects are passing in the same stretch of weeks. What is unusual is that we are looking, and the reason both of these stories are worth telling is not that they signal danger, but that each one, in a different way, pulls back the curtain on how our watching actually works, and on its limits. To really understand how routine this traffic is, consider what is moving past us in just the same stretch of days around this one famous flyby. The catalogue of close approaches for this very week is not empty. There are other objects sliding past the Earth at the same time, some of them passing far closer than 1997 NC1 will, some of them within a lunar distance or two threading between us and the Moon. The difference is that those nearer ones are small, the size of a house or a bus, objects that would, at worst, make a brilliant fireball and perhaps scatter a few meteorites if they ever came down, and so nobody makes a video about them and nobody loses any sleep. What makes this week's headline object special is the combination, the marriage of real size and real proximity. Small and close is common and harmless. Large and far is common and irrelevant. Large and close, at the same time, is the rare overlap that makes an object worth pointing the great radar dish at, and that overlap is what we have this week. And once you know to look, this steady traffic is genuinely constant. In any given month, multiple sizable objects sweep through near-Earth space, and across a year the count of close approaches runs into the hundreds. the overwhelming majority of them passing entirely unremarked because they are either too small to matter or too far to notice, or both. This is simply the nature of the neighbourhood we live in. The space around the Earth is not empty and serene. It is busy, crisscrossed with the orbits of countless small bodies left over from the building of the planets, and our world ploughs through that traffic continuously, year after year, as it has for billions of years. Most of it misses by enormous margins. Some of it does not. The dinosaurs found that out, and the only thing that has changed in the last few decades out of all that span of time is that one species on the surface has finally started keeping a list. So when two large flagged objects make news in the same week, the right reaction is not alarm at a sudden swarm, because there is no swarm. The right reaction is something closer to recognition, the dawning awareness that this traffic has been here all along, steady and indifferent, and that we are only now, in our own lifetimes, developing the eyes to truly see it. The two objects are not a warning that the sky has changed. They are a sign that we have changed, that we are watching more closely than any generation before us ever could. Because look at the contrast between the two objects. With the famous one, the Chaos God, we are facing a future encounter and an interior mystery, a question of what is inside, of how tightly it is held together, of what our gravity will do to it. With 1997 NC1, we are facing an imminent encounter and a surface mystery, a question of how big it is and what its skin is made of, a question that radar is about to answer in days rather than years. One is a stress test of structure we will have to wait for. The other is a reveal of identity that is nearly upon us. And the thing they share, the thread that runs through both, is that in each case we are looking at an object we have known about for years, that we have catalogued and flagged and followed, and that we still, even now, do not fully understand. If that is the state of our knowledge for the objects we are watching closely, the ones that make the headlines, then the objects that never make the headlines should occupy your imagination far more than they probably do. And here is something else worth holding in mind, because it puts this whole moment in perspective. While all of this is happening, while this object closes in for its 400-year visit, the rest of the sky is, frankly, quiet. The sun, which is the source of so much of what we cover on this channel, the flares and the storms and the great eruptions of plasma that can rattle our technology, has been relatively calm. There is no great geomagnetic storm bearing down on us this week, no solar tempest, no incoming wave of charged particles, and in a way that quiet is fitting, because it leaves the stage entirely to this one object. There is no competing drama in the sky. There is just this single, ancient, ambiguous body, drifting in out of the dark after 4 centuries away, carrying its unanswered questions with it, while we scramble to point our instruments at it before it recedes again into the distance for another lifetime and beyond. Because that is the other thing about this past that gives it weight. We do not get to do this again any time soon. This is the closest 1997 NC1 has come to us since before the telescope was even invented, and after June 27th it will pull away again, shrinking back into a faint and distant point, not to return this close for a very long time. So this is not a leisurely study we can repeat next month if we miss something. This is a narrow, precious window. The radar campaign, the amateur observations, the careful measurements, all of it has to happen now in these few days, because the geometry that makes it possible is fleeting. The object that has been a mystery for 30 years is giving us one clear chance to solve it, and then it is gone again. Everything now comes down to a handful of nights, and to what we manage to learn while the door is open. So let us go to that moment. Let us talk about what actually happens when the beam goes out and the return comes back, and about what each possible answer would mean. Because depending on what the radar finds, the object that has worn 3 different faces for 3 decades is about to settle, at last, into just one. And whichever face it turns out to be, it will tell us something not only about this rock, but about how good and how lucky our guesses have really been. Part 10. The Reveal. Picture what is actually going to happen in the high desert. The great dish swings around on its mount, a structure of steel and machinery weighing more than a fully loaded jumbo jet, and it locks onto a patch of empty-looking sky where the calculations say the object will be. The transmitter powers up, and an intense narrow beam of radio energy leaves the dish, racing outward at the speed of light. It crosses the distance to the asteroid in a matter of seconds, far faster than anything we could ever send physically, and it washes over the object. this thing we have never truly seen, illuminating it in a kind of light our eyes cannot register. And then a fraction of that energy bounces back, scattered off every ridge and slope and hollow of the surface, and it races home across the same gulf, growing fainter every second, until it falls back into the dish as the ghostliest of whispers, and the machine listens, and the data begins to flow. And in that returning whisper is the answer to everything. Within hours, as the measurements come in and are processed, the size argument that has stood for 15 years simply ends. The radar gives the diameter directly, and one of two stories becomes true. Either the return comes back from a relatively compact object, confirming the smaller, stonier readings, and we learn that 1997 NC1 is a few hundred meters of rock with a surface that, for whatever reason, was throwing us off, and that bright reflectivity finally gets explained. Or the return spreads out across a larger delay, a bigger object than the small estimates allowed, and we learn that this is a kilometre-scale body, that the dark interpretations were right all along, that we have been watching a genuine mountain. Whichever it is, the number arrives, and it does not arrive as a guess wrapped in error bars wide enough to drive a truck through. It arrives as a measurement, and the shape comes with it. This is the part that always gives me a small chill in the best way. Out of the return, astronomers will assemble an actual picture, a model of the thing turning in space, and we will see for the first time what 1997 NC1 looks like. We will find out whether it is a single rounded body or two lobes joined at a narrow neck, a shape we have found surprisingly often among these objects, a sign of two pieces that came together gently long ago. We will find out whether it spins slowly or tumbles in some complicated way. We will find out whether its surface is smooth or savagely cratered, whether it is solid or a loose pile of rubble held together by little more than its own feeble gravity. 30 years of seeing nothing but a point of light, and then, in a single campaign, a face, a real face with real features on an object that has been faceless to us for an entire human generation. And the shape, when it resolves, will carry a whole hidden history with it, because the form of one of these objects is a record of everything that has happened to it. If the radar shows us a contact binary, two lobes joined at a neck, then we are looking at the frozen evidence of two separate pieces that drifted together and touched so gently they did not shatter, a slow-motion union that happened in the distant past and left this double-lobed monument to it. If instead we see a single rounded body bulging at its equator, that tells a different story, of an object spun up over ages by sunlight until its own loose material slid toward the middle, the signature of a rubble pile reshaping itself under the same thermal forces we have been discussing. And if we see broad concavities, great scalloped bites taken out of the surface, those are the scars of ancient collisions, craters on a body small enough that the impacts which made them nearly tore it apart. The shape is not just a shape. It is a biography written in stone, and the radar is about to let us read it. The way it spins will tell us something too, and there is a strange and important limit hiding in the rotation. Rubble piles, those loose aggregates held together only by their own weak gravity, cannot spin past a certain rate without flinging themselves apart. If you find an object spinning slower than that limit, it is consistent with a loose pile of gravel barely holding hands. But if you find one spinning faster than that limit, and somehow staying together, then it cannot be a mere rubble pile, because loose rubble at that speed would already have come apart. It would have to have some genuine internal strength, some cohesion holding it as a single body. So simply by measuring how fast 1997 NC1 turns, the radar can tell us something profound about whether it is a solid coherent stone or a flying pile of debris, which feeds straight back into the question of what it is and how it would behave. One number, the spin rate, quietly settles an argument about the object's very nature. All of this, the size, the shape, the spin, the surface, the structure, the biography, comes flooding in within hours of the beam reaching the object, and that is what I want you to hold on to as the 27th approaches. We have spent nearly 30 years with almost nothing, with a single ambiguous dot and 3 contradictory guesses, and then, in the span of an afternoon, the floodgates open, and we learn more about this object than in all the decades that came before combined. It is one of the most concentrated bursts of discovery you will ever see in science, an entire identity resolved in a single sitting, and it is happening in days. And then there is the question, that the louder voices have been asking, the one about whether this is a rock at all, and I told you it would be answered on camera, and here is how. As that shape model resolves, it will look like something. And what natural asteroids look like is irregular, lumpy, asymmetric, pocked with craters. Exactly the messy, unplanned geometry you would expect from billions of years of collisions and accretion. If that is what the radar shows, and the overwhelming expectation is that it will, then the artificial hypothesis quietly dissolves. Not because anyone shouted it down, but because the object itself answered. And in the vanishingly unlikely event that the radar showed something else, something smooth, something with the clean geometry of a made thing, then this would instantly become the most important observation in the history of our species, and we would know within days. That is the beauty of it. We are not being asked to believe or disbelieve. We are being asked only to wait a few more days and look at what comes back. The data does not have an agenda. It just has an answer. I think about the people who will be in the room, or watching the feeds remotely as those first measurements come through, and I think about the strange privilege of the moment. They will be the first humans ever to know how big this object truly is, the first to see its shape, the first to be able to say, with confidence, what it is made of and which of the three competing identities was the real one all along. A question that has stood unanswered since the 1990s, that has survived the careful attention of skilled observers for nearly 3 decades, is going to fall in an afternoon. And the rest of us will get to follow along as the picture sharpens and the old debate finally closes, and as one more object in the sky goes from being a half-known rumour to being a known world. But I do not want us to lose the thread in the excitement of the reveal, because the reveal, as satisfying as it is going to be, is not actually the point. The point is everything the reveal implies about all the objects that will never get a reveal like this. We are about to solve 1997 NC1 not because we were clever enough to solve it from a distance, but because it happened to come close enough to touch. We got lucky with the geometry, and that should make you wonder about all the objects whose geometry never lines up this way, all the bodies that stay forever too far to reach with radar, that remain forever nothing but ambiguous points of light, carrying their true sizes and their true natures with them, unmeasured, uncertain, just outside the limit of what we can know. This week we get to answer the question for one of them. The harder truth is how many of them we may never answer it for at all. Part 11. How little we actually see. Step back with me for a moment, all the way back, and look at the whole shape of what we've been talking about, because when you assemble the pieces, a single uncomfortable picture comes into focus. We have a sky we can only search at night. We have an entire direction, toward the sun, that we are essentially blind to, a direction out of which a city killer once came without a single moment of warning. We have a population of large objects of which we have found most of the very biggest, but only a fraction of the merely enormous, and a far smaller fraction of the ones that could still ruin a region. We have a hard wall on how far into the future we can predict even the orbits we know, a wall only about a century out. And on top of all of that, we have just spent this entire video on a single object, one of the ones we did find, did track, did flag, did watch for 30 years, and discovered that even for that object, the one we did everything right with, we still cannot say how big it is or what it is made of until it comes close enough to physically touch. Put all of that together and you arrive at a realization that is, I think, genuinely humbling, and that almost nobody walks around carrying in their head. We do not really see the sky. We see a thin slice of it. We see the bright things, the close things, the things that happen to drift through our narrow windows of attention at the right time of night and the right angle to the sun. And beyond that slice, in the daytime glare, in the far distances, in the future past our 100-year horizon, there is a whole population of objects about which our knowledge fades from confident to rough to frankly speculative to nothing at all. The catalogue of known objects is not a map of what is out there. It is a map of what we have managed to notice, and those are not the same map. The difference between them is the measure of our blindness. And there is a whole other category of threat that the asteroid surveys barely touch, which makes the picture even more humbling, and that is the comets. The objects we have been talking about, the near-Earth asteroids, mostly live in our part of the solar system permanently, looping around the sun on orbits we can learn and track, which is why we can build a catalogue of them at all. But the long-period comets are different. They fall in toward the Sun from the far outer reaches of the solar system, from an immense distant shell of icy bodies far beyond the planets, and they do it on enormous orbits that take thousands or even millions of years to complete. We do not see them coming until they are already falling inward, and by then we might have only months or even just weeks of warning before they cross our part of space. They are typically large, they move terrifyingly fast, and they arrive with almost no notice. There is no survey that can map them in advance, because they spend almost all of their immense orbits out in the dark where nothing can see them. They are, in a real sense, the threat we genuinely cannot prepare for, and they are a reminder that the asteroid catalogue, impressive as it is, covers only one kind of danger. When you stack it all up, the asteroid blind spot toward the Sun, the incompleteness below the largest sizes, the 100-year prediction wall, and now this whole separate population of comets that can fall in on us almost unannounced, you start to see just how partial our map really is. Imagine an old explorer's chart of a continent, with a thin band of carefully drawn coastline and then, just inland, the lettering trailing off into blank parchment. The famous emptiness where the mapmakers simply did not know. That is roughly the shape of our knowledge of the objects that share our space. The coastline, the close and large and well tracked, we have drawn beautifully. But the interior, the far and the faint and the future and the comets, fades quickly into blank parchment. And the thing about blank parchment is that it is not empty in reality. It is only empty on the map. The things that live there are perfectly real. We simply have not drawn them yet. Now, I want to hold this in balance, because the channel does not deal in despair any more than it deals in panic, and the balanced truth is that we are not helpless and we are not standing still. The very fact that we can tell this story, that we know about the blind spot, that we can quantify how complete our catalogue is and where it falls short, that we have a great dish in the desert that can reach out and measure an object directly, that we are building a new telescope to finally watch the sunward sky. All of that is the product of people who looked at our blindness honestly and decided to do something about it. Knowing the limits of your vision is the first and most important step toward extending it. A civilization that understands exactly where its blind spots are is in a far stronger position than one that imagines it sees everything. We are slowly, patiently lighting the dark corners. This week, with this object, we are lighting one of them. But the lighting is slow and the dark is large, and 1997 NC1 is, in the end, a reminder of both. It is a reminder of how much we can do, because we are about to solve it completely, to drag it from mystery into knowledge in a matter of days. And it is a reminder of how much we cannot do, because the only reason we can solve it is that it chose, in effect, to come close, and most objects never do. It is both the triumph and the limit of planetary defense wrapped into one passing rock. And as it makes its closest approach, as the radar reaches out and the answer comes home, I think the right response is not fear, and it is not complacency. It is a kind of clear-eyed wonder, the recognition that we are a young species just beginning to learn how to truly watch the space we live in, getting a little better every year, and still, for now, seeing so much less than we like to imagine. So as we come to the end of this, and as 1997 NEC1 bears down on the closest point of its 400-year journey, I want to leave you not with the question of whether this object is dangerous, because it is not, and you can sleep soundly on the 27th. I want to leave you with the deeper question that this whole strange episode has been circling from the very first minute. Not what is this rock? We're about to learn that. The real question is the one the rock has been asking us all along, simply by being so close, so large, so long known, and so completely unidentified. And it is a question not about the object at all, but about us. Part 12. What we're about to learn about ourselves. Here is the question, stated as plainly as I can state it. How does something this big stay this unknown for this long? That is the real mystery of 1997 NC1. And notice that it has nothing to do with whether the object is dangerous. We have settled that. It will miss us by 2.5 million kilometers, and you can mark the 27th on your calendar as a night of wonder rather than worry. The mystery that actually matters is the one hiding behind the safe miss. We are about to discover that an object somewhere between the size of a stadium and the size of a small mountain, an object on an orbit that crosses our own, an object we found nearly 30 years ago and have watched ever since, has spent that entire time as a question mark, its size uncertain by a factor of 4, its very composition disputed 3 ways, until the lucky accident of a close pass finally forced an answer out of it. And if that is true of the asteroid we know best, then the catalogue we have been quietly trusting to tell us we are safe is a great deal blurrier than its neat rows of numbers suggest. I find that I cannot decide whether this story is reassuring or unsettling, and I have come to think that the honest answer is that it is both, fully and at the same time, and that holding both is the mature way to look up at the sky. It is reassuring because we did find this object, because we are about to understand it completely, because the largest civilization-ending bodies are mostly mapped, because there is a dish in the desert that can reach across millions of kilometers and read the truth off a passing rock, and because there is a new eye being built to stare into the one direction we have always been blind. We're not the people of the 1600s, the last time this object came around, who could not have seen it coming and would not have understood it if they had. We see, we measure, we reach out and touch. That is an extraordinary thing for a species to be able to do, and it is barely a few decades old, and it is unsettling for exactly the same reasons, turned over, because we found this object and still did not understand it, because the largest bodies are mostly mapped, but mostly is not all, and the merely enormous ones are largely uncharted, and the sunward sky is a curtain we have not yet pulled back, because the dish in the desert can only read an object that comes close enough to touch, and most of them never will, because the new eye is not yet open. We are in the end a young species that has just barely learned to watch its own neighbourhood, that can do remarkable things in the narrow slice of sky it can see, and that is still, if it is honest, mostly in the dark. 1997. NC1 is the proof of both halves at once. It is the object we are smart enough to solve, and the reminder of how many we are not yet able to even find. So when it makes its closest approach, I'm not going to be thinking mainly about the radar measurements, satisfying as they will be, and I'm not going to be thinking about the old argument finally ending, gratifying as that is. I am going to be thinking about the 400 years, about the fact that the last time this rock was this close, no one on Earth could have known it was there, and about the fact that this time, we do. We caught it. We named it. We followed it for 3 decades. We argued about it. We pointed the finest instruments we have ever built at it, and on a few precious nights we're going to drag it out of mystery and into knowledge, while ordinary people in their backyards watch the same faint speck crawl across the stars. That gap between the blindness of the 1600s and the sight of today is the whole story of what we have become, and the darkness still waiting past the edge of that sight is the whole story of what we have left to do. The rock will pass. It will brighten in our telescopes, give up its secrets to the beam in the desert, settle at last into a single known shape and size and nature, and then it will pull away, shrinking back into the dark, not to return this close for longer than any nation now alive will exist. And we will be left with the answer, and with the question the answer raises, which is the only question worth carrying out of all of this. We have learned to see a sliver of the sky with remarkable clarity. The rest of it, the far distances, the daytime glare, the centuries past our horizon, is still mostly unmeasured, still mostly unknown, still mostly waiting. The asteroids do not care whether we are watching. They have never cared. The only thing that has ever changed, the only thing that is ours to change, is how much of the dark we are willing to learn to see. And every time one of these ancient visitors drifts close enough to touch, it asks us the same quiet question, the one 1997 NC1 is carrying toward us right now, across the last 1,000,000 kilometers of its long way home. Not whether it will find us, but whether, when the next one comes from the place we cannot look, we will have finally learned to find it first.